Okay, so start writing the topic, the rotational motion. Okay, so first we will understand the key terms like angular displacement, angular velocity, and angular acceleration. Angular displacement is what we now in linear motion, the objects we consider it's move in a straight line. Okay, but in rotation motion, it move in a, if you take a particle, it move in a circular path. Okay, now for example, you get the okay. So let's say there is a particle moving in a circular path. Say at t equals 0, the position of the particle is here. So after some time, say time equals t, the particle is here, then its angular displacement is the angle it has been made by the center of the circle. So this theta is the angular displacement, the angle, how much of it's rotated. The angle it has been rotated is the uh, angular displacement. Now, for example, an object moving in a circular path, then the angular displacement is theta. Or else you can consider, for example, a circular disk, and then I'm rotating. Or for example, let's say this is the point A on the disk. Okay, it's a horizontal. Then I'm rotating the disk so that the point A comes to here. So in that case, again, there is a angular displacement theta. Okay, so the angle through which a point or line has been rotated. Now, when it's particle moving in a circular path, then we can consider a point is moving. Okay, point is rotated. Okay, or else if we consider a body or object, then now we have this line. Okay, so this line is being rotated by the angle theta. So that angle is the angular displacement. Okay, and then angular velocity. So that is the rate of change of angular displacement. Now in linear motion, the velocity is the rate of change of displacement. So in angular rotation motion, so angular velocity is the rate of change of displacement. Okay, so the rate of change of displacement, so omega is the angular velocity, the change in displacement delta theta over delta t. Okay, the rate of change of angular displacement. Okay, and by the way, the angular displacement is measured in radians. So normally we deal with radians. If in case in a question they have asked to find the angular displacement in degrees, then you have to convert the radian into degrees. Okay. Okay. And angular velocity is delta theta over delta t, the rate of change of angular displacement. And angular acceleration, we have alpha. Alpha is the rate of change of angular velocity, delta omega over delta t, the rate of change of angular velocity. It is very similar to the linear motion. In linear motion, the velocity is the rate of change of displacement. Then in rotational motion, the rate of change of angular displacement. And acceleration is the rate of change of velocity Then in rotational motion, the angular acceleration is the rate of change of angular velocity. Okay, so you can write down this angular displacement and angular velocity and angular acceleration. So under the angular displacement, you may draw this figure, and this theta is the angular displacement. Okay, so the angular velocity omega is equals to rate of change of angular displacement delta theta over delta t. So the angular displacement measured in radians, right, divided by delta theta is in seconds time. So therefore the unit of omega will be rad per second. So rad per second is the unit of angular velocity. And then angular acceleration alpha is equals to rate of change of angular velocity delta omega over delta t. And its unit will be, what is the unit? So angular velocity is measured by rad per second divided by time seconds. So then we get rad per second squared as the unit of angular acceleration. Okay. And I'll ask you a question. What about these quantities? Are they vectors or scalars? Angular displacement. Okay. Tell me angular displacement is a vector or scalar? I need a response from each and everyone. By the way, if anything you want to text, you can text to the Knowledge Institute. So it will be easy for me to view. Okay, I'm getting mixed answers. Okay, so angular displacement is a type of displacement. We know in general displacement is vector. So therefore angular displacement is vector. So therefore here this theta is a vector. Angular displacement is vector quantity. Okay, because it's a type of displacement. So displacement is in general, it's a vector. So therefore angular displacement is vector. And what about angular velocity? Is it a vector or scalar? Yes. So angular velocity is a vector. So the omega is a vector quantity. And also angular acceleration is also a vector. So all three are vector. And I want you to write the dimensions of each of these. So what is the dimension of theta? You had to write in your book and snap a picture and share your answer through Zoom chat. Okay. The dimension of these three: theta dimension and omega dimension and alpha, dimension of alpha. So write the dimension of theta, omega, and alpha, and take a snap and share your answers to the Zoom chat. If you are not able to send through the Zoom, then you can share your answers through WhatsApp. Because I want you to understand, because I want to know how much you have understood well the dimension lesson. Okay, I got the answers from one student. Okay. I'm expecting the answers from everyone. Okay, so I got an answer saying that this is L minus 1, this is S minus 1, this is minus 2. Okay, so here actually uh, theta is measured in radian. So we know plane angle have no dimensions, so it's dimensionless. So I think Hirosh has mentioned, yeah, I saw your one, Hirosh. Hirosh has mentioned this as dimensionless. But if you write like this, you will get wrong because it is actually dimensionless quantity. So the dimension of dimensionless quantity is 1. Okay, so here it has to be 1. And then omega is actually the unit rad per second, right? So the radian doesn't have a dimension because it measures the plane angle. Plane angle have no dimensions. So then, but here t minus 1, the per second is measured in t minus 1, and here it is t minus 2. So these are the dimensions. Okay, the plane angle is dimensionless quantity, so its dimension is 1. Okay. Okay, so I hope you have wrote all of these. If in case you didn't complete it, you can take a screenshot. Okay. So then now here, I'll give all the quantities that we will be using in rotation motion. So theta is the angular displacement. Angular displacement. and omega naught is the initial velocity, initial angular velocity. And omega is the final angular velocity. And alpha is the angular acceleration. And t, as usual, time. So here these all are vectors except only the time is scalar. So quantities involved in rotation motion. You can write this down. Okay. So then the relation between linear and rotational quantities. Now this is the linear displacement. We know the linear displacement is given by S. So S and the angular displacement is theta. Okay, the relation between these two is given by S equals R theta. Okay, so I'll explain that. So let's say a particle is moving in a circular path. So here this angle is theta, and this is the linear displacement. Actually, when it comes to linear displacement, it's a straight line. So this radius is R, and this S. So it can be both. You can mark either this straight line or this curved line. We just take as S displacement, the linear displacement. So that is given by S equals R theta, the relation. Theta is the angular displacement, S is the linear displacement, and R is the radius. And if it's moving in a circular path, then the radius of that circular path. Okay, and then angular velocity. So we know velocity is the rate of change of displacement. Now the change in displacement, I can write delta S. Now if it's moving in a circular path, the radius won't change. Okay, the displacement vector, I mean the position vector R remains change, radius is constant, but the angle is changing, delta theta. And if I divide both sides by delta t, so delta S divided by delta t is the linear velocity, is equals R times delta theta over delta t is the omega. So therefore V equals R omega. And we know that then I can find the change in velocity delta V equals R times delta omega. And then I'll divide this both side by delta t. Then delta v over delta t, the rate of change of velocity is the acceleration, equals r times delta omega over delta t is the angular acceleration, alpha, A equals r alpha. Yeah, okay. The previous equation means this is equals r theta, right? You mean? Then you mean this one? Okay. So the relation between the linear displacement and angular displacement is given by S equals r theta. So now I consider a change, some change in displacement. So delta S is equals to r times delta theta. Because if S is changing means the delta theta will change. So but r is constant. If it's moving in a circular path, r is constant. Therefore delta S is equals to r times delta theta. And then I divide both sides by the time, the change in time delta t. So delta S over delta t. What is this? This is the rate of change of displacement, which is velocity. Okay, is equals to r times rate of change of angular displacement is the angular velocity. So therefore we get V equals r omega as the relation between the linear velocity and the angular velocity. So V equals r omega is the relation between linear velocity and the angular velocity. Okay, and then again I can consider for change, some change in delta V is corresponds to r times change in delta omega. Okay, and then I divide this both side by again delta t. So here rate of change of linear velocity, rate of change of velocity is the acceleration, equals r times rate of change of angular velocity is the angular acceleration, alpha. So A equals r alpha gives the relation between the linear acceleration and the angular acceleration. So S equals r theta, V equals r omega, A equals r alpha. So the relations are very straightforward. You can see the linear displacement is r times angular displacement. Linear velocity is r times angular velocity. Linear acceleration is r times angular acceleration. Okay. All right. So you can write down this. Take a screenshot and write. So r is the radius of rotation. Now, for example, if we are talking about a ball rotating, so the radius of the spherical ball, or a disc is rotating, the radius of the disc. Or for example, if I consider a rod is rotating about its center, then its half a length will be the radius. Okay. Okay. Okay, so normally the motion we can describe as two things, kinematics and dynamics. Kinematics means we only consider the movement of the center of mass, how it varies, what it will be the velocity, what is the displacement after some time. what is the acceleration, okay, what is the final velocity. So these the motion of the center of mass we describe in kinematics. Dynamics means what causes this motion, like the force, and then the weight, I mean the forces acting on it, it's the dynamics. Okay, what causes the motion is dynamics, and then the movement of the projectile is the kinematics. Okay, so rotational kinematics deal with motion of object without considering the forces causing the motion, because when we consider the forces it comes to the dynamics. So here only we consider the kinematics, like what you have studied in equations of motion in the previous lesson, right? The equations of rotational kinematics are analogous to linear motion equations. Okay, so there are four equations of motion that we studied in linear motion, right? So those are V equals U plus AT. And then we have V squared is equals U squared plus 2AS, and S equals U plus V divided by 2 into time. And finally we have S equals UT plus half AT squared. So these are the equations that we studied in equations of motion in right. So here in rotation motion we have similar set of equations. So final angular velocity, when it comes to rotation motion, then all terms comes to angular. So angular velocity, the final angular velocity omega equals omega naught initial velocity plus alpha t. Omega squared equals to omega naught squared plus 2 alpha theta, and theta equals to omega plus omega naught divided by 2 into time. The same equation, but we are changing the symbols. Now here it's linear velocity, here angular final velocity, here linear initial velocity. And here theta is equals to omega t, sorry, omega naught t is initial velocity plus half alpha t squared. Okay, so you can write this down. So these are the equations in linear motion. And these are the equations in rotation motion. Okay. To check your previous knowledge, I'll ask a small question. What is a linear motion? Let's see who can answer correctly. A linear motion or rectilinear motion or straight line motion, all same thing. Linear or rectilinear or straight line. Linear motion or rectilinear motion or straight line motion. So what is a straight line motion? Okay, I got an answer from Hirosh. Hirosh's answer is correct. An object moved in a linear or straight line path, that is not accurate explanation, because an object moving in a straight line doesn't mean it is a linear motion. Now, let's say there is a particle, it's moving in a straight line, or car, if I take the car is moving in a straight road, but doesn't mean it is a linear motion. There's a definition for linear motion. Okay, so the linear motion means uh, the object is moving under constant acceleration. A is constant. If A is constant, then we say that motion is linear motion. Now, for example, let's say the car is moving in a straight line, but it's accelerating and stopping, and then again going with different acceleration. The velocity is changing, like the acceleration is changing, then it is not a linear motion. So, therefore, a car moving in a straight line doesn't mean it is moving in a linear motion. We can't say it's in a linear motion. Motion is linear only if its acceleration is constant. So constant means, now for example, it can be A can be equal 0, so because it's also 0 value, right? It's a constant 0 value, A equals 0. That means moving at uniform velocity. So moving at uniform velocity is a linear motion because A is constant. Or it can be moved with constant acceleration of 2 meters per second squared, where the velocity increases by 2 each second. So 2 meters per second and then 4 meters per second, 6 meters per second. The velocity is gradually increasing. So that is also linear motion. Now, for example, I take a stone and throw. So it goes in a parabolic path. Now you can see the path, that this parabolic path, it is not a straight line, right? It is a parabolic shape, but it is a linear motion, straight line motion, because it's moving under constant acceleration, which is pointing downward. Uh, G, the gravitational acceleration, has a value of roughly 10 meters per second square. So an object, when an object moving under constant acceleration, then we can say that the object is in linear motion or straight line motion. Okay. So if you got a question, what is a straight line motion? Then the answer should be the object is moving under constant acceleration. The word constant acceleration is must. Okay. Okay. So now in think when we discussing about the equations of motion, okay, we wrote that these equations can be applied only if the acceleration is constant. Sorry, A is constant. Similarly, we can use the set of rotational motion equations only if the A is constant. Rotational motion. So then alpha is constant. Okay. So after writing this, you can write these equations are valid only if alpha is constant. These equations are valid only if alpha is constant. So, for example, alpha can be 0 also can take, because when alpha is 0, if for example you take this first equation, omega equals omega naught plus alpha t. If alpha equals 0, this term 0, so omega equals omega naught. That means final velocity is equals to initial velocity, meaning that no change in velocity, the object is rotating with constant angular velocity. So the angular velocity of the object is constant. Okay. Okay. Now let us write down these, try these questions. So you have to use this set of these 4 equations. Okay. A wheel starts from rest and has angular acceleration of 2 rad per second squared. This. Calculate the angular velocity after 5 seconds. Okay, do this question. And please share your answers. Very good, Asha. Your answer is correct. Yes. So then here we can use the equation omega equals omega naught plus alpha t. Okay. By the way, I told you these are vectors. For example, theta, omega, alpha. These are vectors. So vectors means they have both magnitude and direction. So the magnitude, now we know how to calculate, right? So for example, if object rotated 60 degree or let's say 90 degrees, so then the angular displacement is 90 degrees. That's the magnitude. Okay. So in radian, 5 over 2, right? 5 divided by 2. If 90 degrees means in radian, it will be 5 over 2. So that's the magnitude. Then what about the direction of the angular displacement? Now let's say mm, so a particle from here, it has moved to here. So then angular displacement theta magnitude is 5 over 2. Okay. Then what about its direction? Can someone what about the direction? Because vector means it should have both magnitude and direction. Okay, so to find the direction, we can use the right hand rule. So if it's rotating anti-clockwise, okay, so then you keep the right hand like this and then anti-clockwise. So according to this figure that I have illustrated, so it's, let's say, moving in this direction, omega, and then this is the angle, okay, the rotation angle is 5 over 2. So the magnitude is 5 over 2, and then if I use this right hand rule, it's coming out of the screen. So from the direction is from the center point, on this point O, it is coming out of the screen. But in our 2D plane, we can't mark that direction. So normally we mark as, uh, so if it's coming out of the screen, it is then actually anti-clockwise. So anti-clockwise makes coming out of the plane. But if I take clockwise, so if it's moving clockwise, then it is into the screen, into the plane from the O. So normally in when we writing in book and all, we mark as clockwise, anti-clockwise, but actually the direction is not clockwise. The vector direction is not clockwise and counterclockwise. It's a intuitive way that we can mark in the book. So if it's clockwise means it's coming out of the screen, the actual direction. So anti-clockwise means coming out of the screen. Clockwise means it is into the screen. Okay, like how we deal with the torque. Okay, tau equals r into d, r into f, or d into f, the perpendicular distance into force. So the torque also have the direction from the center, from the pivot point, either in out of the paper or into the paper. Again, we normally mark counterclockwise or clockwise, right? Okay. So here we can use omega equals omega naught plus alpha t to find the final velocity after 5 seconds. So omega equals omega naught is starting from rest 0 plus alpha is 2 rad per second into time 5. So therefore omega equals 10 rad per second. Okay, so that 10 rad per second is the magnitude, and then direction. So here no need to mention a direction because in the question they haven't particularly mentioned a direction. Like they haven't mentioned rotating counterclockwise or clockwise scale. So therefore no need to mention, just only find the angular velocity after 5 seconds. That's it. Okay, and do the question number 2. Yeah, that's correct. Now, Aida, if I correct me if I spell your name correctly. Okay. So she has used this final velocity using this alpha equals the rate of change of delta omega over delta t. She has used this equation. So then alpha is actually delta omega is final velocity minus initial velocity change the time t. So in this equation, if you subject omega, you get this equation because this equation is derived using the definition of alpha. Okay, so that's correct. Okay. Question number 2, a disk rotates with the initial angular velocity of 10 rads per second and decelerate uniformly to rest in 4 seconds. Find the angular displacement during this time. Okay, do this question. So first you had to choose which equation to be used. Got the answers from Hiroshi, Aisha, and both seem to be the same answer, so I think it might be correct. Okay, a disk rotates with an initial angular velocity of 10 rads per second and decelerates uniformly to rest in 4 seconds. Find the angular displacement during this time. Okay, so here we can use the equation that theta equals to omega naught t plus half alpha t squared. So theta equals omega naught initial velocity is 10 rad per second into time 4 seconds 4 plus half into acceleration decelerates uniformly to rest. Okay, so here the deceleration is not given, so I can't use this equation. So I use the third equation, theta equals omega plus omega naught over 2 into time. This is the equation I had to use since theta is not given. So here theta is equals to omega. Final velocity is 0 plus initial velocity 10 and then divide by 2 into time is 4 seconds. So therefore theta is equals to 10 divided by 2 is 5 into 4, 20. The units is rad, 20 radians. Okay, because you can see the angular velocity is given in radian per second. So then if you multiply by the time, you get in radians. Okay. Okay. Now, what if I ask you, what is this angle in degrees? Find this angle in degrees. Okay. So I want you to convert 20 rad into uh, degrees. Find this answer. Find 20 rads in degrees. Okay, so first, what is the relation between phi and radian? We know phi e phi rad equals 180 degrees, right? So then 1 rad equals 180 divided by 5. Okay, so 180 divided by 3.14, something like 50. We wrote that in, and we no need to find the value here. You can just convert. So here 20 rad, okay, 20 rad is, I can write 20 into, so radian convert to degree, 180 over 5. So it will be first that 180 divided by 5. 57.3 roughly. So this is actually 57.3. So 20 into 57.3. This part 20 into 57.3. 1146. 1146 degree angle. Okay. And I'll ask one more question here. So this is the this angle 20 rad in degrees. Okay. So the next question, how many revolutions that disk has made? How many revolutions? Revolutions. That means rotations. Okay, revolutions. How many revolutions disk has made? Okay, good. So this is the total angle that is being rotated, because one revolution is 360 degrees, right? So this number I have to divide by 360. So this number is actually we got from here, 20 into 180. Okay, uh, divided by 5. This whole number we have to divide by 360. So this one I can rearrange and write 2 into 180 is 360 into 10. Here divide by 5 divided by 360. So 360 and 360 cancel. 10 divided by 5. So 10 over 5. So 10 divided by 5. 3.18. So 3.18 revolutions. You can keep as this standard, not a standard but acceptable unit. Okay. So 3.18 revolutions. Now, for example, 3.5 revolutions means it will be 3 complete rotations and 1 half rotation. Now, for example, let's take this tip. Okay. So let's say it's rotating about this point. So it will go 1 cycle means 1 revolution, and 2 cycle means 2 revolutions, and 3 cycle means 3 revolutions, and another half revolution. Half revolution means 180 degrees. So that is 3.5 revolutions. But here it is 3 revolutions and some small angle has been made. Okay. Okay. So can we keep without decimal as only 3? Now here one student is asking, is it okay to keep it as 3? Now, if the question asks how many complete revolutions has made, then you can say 3 revolutions. Okay. So, but here the total revolution is this. So then you should write 3.18, but you can't write as 3. It will be wrong. But if they ask in the question how many complete rotations has been made, then you can say 3. Then it is correct. Is that clear? Okay. If you have any questions, you may ask. Okay. I'll be wiping the screen. And question number 3. An object completes 20 revolutions in 10 seconds. Calculate its average angular velocity in radians per second. Okay. I'll ask you one question first. One revolution means what is in radian? One revolution is equals to in radian how much? Yes, good. What about others? Now, for example, this if I take one complete rotation, this actually going 360 degrees, right? So 360 degrees in radian, we know it is 2 pi. So one revolution is equals to 2 pi rad. Okay, but an answer 10 rad per second. Let's see. Okay, so now here we have it's moving at constant velocity, constant because we have taking the average velocity. So average angular velocity omega average is equals to total displacement over total time, right? So in normally the average velocity, okay, average velocity, do we calculate total displacement over total time. So similarly, total angular velocity, sorry, average angular velocity, average angular velocity is equals to total angular displacement divided by total time. Okay, so therefore total displacement over time. So total displacement is an object completes 20 revolutions. So 20 into one revolution. So one revolution into 20 is 20 revolution. But by time is 10 seconds. So 20 to one revolution is equals to 25 radian. One complete rotation is 25 rad divided by time 10. So 20 divided by 10 is 2. 2 into 2, 4, 5 rad per second. 4, 5 radians per second. Okay. So that's the answer in radian per second. So they are asking in radians per second. So it's radian per second. So no need to convert. Okay. So if you want, you may note down this that average angular velocity is total angular displacement divided by total time. Yeah. So the answer is 4-5 radians per second. Okay. And let's move to the next question. A fan blade increases its angular velocity from 5 rad per second to 15 rad per second in 3 seconds. Determine the angular acceleration. Okay, do the question. Okay, good. So the angular acceleration alpha we can find omega minus omega naught divided by t. Okay, so final is 15 rad per second minus 5 rad per second divided by time 3. So 10 divided by 3 is equals 3.33 rad. So that's the answer. Sorry, rad per second square. Because rad per second divided by second, rad per second squared acceleration. So radian per second squared. And by the way, here we discuss about the dimensions now. Dimension of theta is 1. Dimension of omega is t minus 1. Dimension of alpha is t minus 2. So here the omega, the angular velocity has the same dimension of frequency. So dimension of omega is equals to dimension of frequency, which is t minus 1. So therefore, the omega is also, the angular velocity is also referred as angular frequency. Okay, so this is known as the angular frequency because it has the same dimension as frequency. So angular frequency is same as angular velocity. If you refer some textbooks, you can find this word they have used instead of angular velocity. Okay, that's another thing. You can do number 5. A wheel rotates with a constant angular acceleration of 4 rad per second squared. If it starts from rest, calculate the angular displacement after 3 seconds. Okay. Anyone got the answer? Okay. You got the answer from either as 72 rad. About others? Okay. So I think 72 rad is correct. I think because I get that. Same answers from 3 students. Okay. So here we can use theta equals omega naught t plus half alpha t squared. Theta equals to omega naught. Initial velocity is 0 starting from rest. So initial was 0 plus half into angular acceleration 4 right per second squared into time 6 seconds. So 6 squared. Theta equals 4 divided by 2 is 2 times 36. Theta equals 72 rad. Okay, find the number of rotations. Find the number of rotations. Okay. Now here it's saying number of rotations, so no need to keep the decimal value. Now in the previous question, find the revolution. So for the find the rotation, then you have to keep the, now here it says the number of rotations, then you just want to find the integer value. Like if it's 3.4 means 3, 4.5 means 4, 7.2 means 7. Okay, find the number of rotations. Okay, so this is the total rotation. Okay, total, I mean revolution. So therefore number of rotations, okay, n say is equals to theta divided by 2 5, because this is the one, the angular displacement of one rotation. So therefore here 72 rad divided by 2 5, 2 into 5. So 72 divided by 2 is 36. So therefore the, so here 2 5 rad unit will cancel, rad and will cancel. So 36 divided by 3.14 approximately. So we have 36 divided by 5, 11.45, 11.46, 11.46. Therefore, number of rotations, so number of rotations is 12. So the wheel rotates 12 times. Sorry, 11. Because 11.46, right? 11 and some half, right? Roughly half, 11.5. So 11 rotations. So the wheel rotates completely 11 times. Okay. If you have any questions related to these angular equations of motion, I mean rotational equation of motion, you may ask. So it's not, it's a normal thing right now. Equations, motions are all normal thing for you, right? So then let's move on to the next lesson. Rotational motion dynamics. Okay. So here we have the summary of what are the things that we have to study under the rotational motion. So the torque. So torque, which is the moment of force, I'm not discussing here because we already discussed that separately, right? We have discussed everything related to the torque. So therefore, we are not discussing that here. Okay. And moment of inertia. So we want to study what is moment of inertia, Newton's second law of rotation, and angular momentum, and work and energy in rotational motion. Okay, so these are the chapters that we want to discuss under the rotational motion. Okay. So let's start with moment of inertia. By the way, how many of you have studied the moment of force lesson? 1, 2, 3, 4, 5, 6. 1, 2, 3. So 6 people are there. Don't put your hands down. Keep face. So 1, 2, 3, 4, 5. What about Ambra? Okay, so glad that everyone has studied the moment of force. So therefore, I can skip that part. So we'll start from the moment of inertia. Okay. So you can write the topic moment of inertia. Alright, done. The moment of inertia, it is denoted by the letter capital I. Okay, so before I'm explaining moment of inertia, we already studied inertia when we discussing about Newton's laws of motion, right? In Newton's first law. After that, after stating the Newton's first law, we discussed what is inertia means. Okay, tell me what is inertia. What is inertia? Okay, I got only one answer. If in case you don't know, please respond as don't know so that I can understand. Right? Resistance to show change in state of motion. Very good. So inertia is the reluctance or the resistance of an object to change its, so I can say to change its either two things I can write. State of motion, to change its state of motion, or simply I can say velocity, because velocity is the state of motion. If the object is at rest, velocity is zero. If the object is moving at constant velocity, so it's a constant velocity in this direction, right? So it's another state of motion. So it's in moving in one direction. And when the velocity change to another direction. So by, let's say the magnitude is 5 meters per second. So it's moving this direction 5 meters per second and then change the direction moving 5 meters per second. So uh, even though the magnitude is same, if the direction changes, velocity will changes. So therefore two different state of motion. Okay. Okay. So therefore reluctance of an object to change its velocity. Okay. Is the inertia. So now this is in the linear motion, like F equals ma, right? So the mass is the measure of inertia, right? This is I equals m. In linear motion, the mass is the inertia, okay? But in rotational motion, it is not the mass. It's a different thing, okay? We will see that, okay? So, uh, Write the topic moment of inertia, a measure of an object's resistance to change its rotational motion. Changes its state of rotational motion. Let's say its state of rotational motion, or in brackets, to change its angular velocity. Reluctance of an object to change its angular velocity. If object is at rest, it has a reluctance to move. So at rest means angular velocity is zero. So it has a resistance to gain some velocity. Okay. Measure of an object's resistance to change its state of motion or to change its angular velocity. Now in linear motion, we know the mass is the measure of inertia. If higher the mass, higher the inertia. Now, for example, I have a beach ball and a large weight. For example, 1 kilogram rice bag. Okay, oh sorry, 10 kilogram rice bag. So it can be easy for me to give a velocity, right, for the ball, beach ball. Just if I give a small kick, it gains a velocity very easily because it has a lower mass. So therefore, it has low uh, reluctance to change its state of motion. So therefore, low inertia. But the 10 kilogram rice have a larger mass. So therefore, it has a larger inertia. So simply in linear motion, the inertia equals to the mass, I equals m. I equals to the total mass, okay, of the object. Now we are discussing the inertia in the rotational motion. So in rotational motion, the inertia is not the mass. I is not equal to mass. It's a different thing. Okay. So the inertia of an rotational motion, rotational body is given by I equals sigma mi ri squared. Okay, so this is the inertia in rotational motion. If you didn't understand about this equation, don't bother. We will explain this thoroughly, okay? But for the moment, you can write down this is the uh, inertia for rotational motion. Okay. Okay, I start with one example. Let's say an object, a stone or a ball, is attached to a string and it is moving in a circular path. And let's say the mass is m, okay, and the length of the string is r, okay. So, and also I consider this is a point particle, even though I have drawn as a ball, it's let's say a point mass, okay. Because if I consider a large mass, okay, like large mass, so the distance will be for each particle will be differ. So if it's a large mass, then we have to consider its center of mass. Only the center of mass we have to consider. Okay. Okay. So then its inertia of this body or the object is given by sigma m r squared. So here we have only one mass. So I take its mass m, and then distance to that mass is r. So therefore r squared. So therefore you can write this as example 1. So that inertia is given by I equals n r squared. And I'll take another example. I say to indicate this is rotating, I will mark the angular velocity omega. So it's inertia about inertia. When we talk about inertia, we had to consider a point about point O. So the rotation moment of inertia of mass m about O is given by I equals mr square. Okay. So that's example 1 and then example 2. And here we have to consider the strings as a typical condition, light and inextensible. Okay. So the string is light. Otherwise, we had to consider the mass of the string also, so which we did not study it yet. Okay. So therefore, here the string is light. Okay, so the second one, here I have a mass uh, m, and here another mass m, and this distance a, and this distance a, and they are attached by light inextensible string, and they are rotating about this axis with the speed o. So it is a string rotating about this axis. Okay. So then according to definition of I equals sigma mr squared. So that means I have to add all the mr squares. Okay. So therefore here I equals to, so the mass of this one is m, and then distance to that is a, ma square plus, and I have another a mass m, and then distance to that is 2a squared. So therefore I equals ma squared plus, here if I square this 4a squared, so 4ma squared. Therefore I equals 5ma squared. The symbol sigma is to add. You have to add all the mr products, mr squared terms. Okay. Okay. Raise your hand if you understood up to here everything. What about Aisha and Abhi? Aisha, Abhi, Shani, did you understand? You have any doubts or questions? Aisha, okay. Abhi, Shani? Abhi, Shani, did you understand? Okay, so here I equals sigma mi ri squared. Mi refers to all the individual masses. Ri refers to the distance to the rotating axis from that point to the mass. Okay, so then now for example, in this example, if you take this mass, the distance from this rotating axis is a. Okay. So then we take m times a squared, mr squared, so m times a squared. And then also we have this mass. So its distance is, mass is m, and the distance is 2a. From here to here, the distance is 2a. So 2a squared. So we get 4ma squared. So therefore, moment of inertia of this system is 5ma squared. Okay. So we can see from this equation, if the distance is larger, it has a large inertia, right? Because inertia is proportional to the distance squared. So if you, for example, if you double the distance, the inertia will be much higher, right? So that is why you may have seen in these circles and all that people used to carry a long rod. The people who walk in the rope, they carry a long rod so that they will get a large inertia because the mass is distributed to very far distance, right? So because the mass is distributing to far distance, so the inertia will be then larger, very large. So therefore what happens, the reluctance to change the state of motion is very large, so they can easily balance because it has a large reluctance to change the velocity. So barely angular velocity will change, therefore they can easily balance. That's why they carry the long uh, bamboo this rod, that stem. You may have seen that, right? Raise your hand if you have seen people doing like this in circus. Hirosh, haven't you seen? Yeah, we okay, good. All right. So these two examples, then I will give you questions. Now here we have actually discrete mass. Here one mass, here one mass. Now, for example, let's say we are rotating an object like this, okay, by about this. Now here the mass is continuous. So for the continuous case, so this extensional work. So extensional work means it's not in the syllabus. Okay. Then the I is actually you have to integrate. Integrate m uh, so it is an integration of you have to integrate yeah, so m, so m we can write times dr squared. It's a second derivation. You have to integrate if it's continuous means. Okay. Okay, but here in our syllabus we only discuss about discrete, and also we will be discussing about continuous, but it's a some regular shape. Now, for example, ring. Okay, so we will see how to calculate these moment of inertia of ring, disk, and all. Okay, so I'll give you some questions you have to find the moment of inertia of each of the following systems rotating about the axis going through the point O. Okay, first question. Okay, I'll give you a similar question here. 2 kilogram, 3 kilogram, 1 meter, 2 meter. It's point O. Mm, So this red color is actually strings, okay, a light rod. They are rotating about the point axis, and you have to find the moment of inertia. Okay, so there are two questions. Quickly do this. Yeah, by the way, I forgot to talk about this. What about the units of inertia? Units. So we can see it's sigma mr squared. So mass is kilogram, and then meter squared. So kilogram meter squared, and then dimension. Dimension is ml squared. And is it a vector or scalar? State whether it's vector or scalar. Everyone? Good. It's a scalar, very good. Because inertia is a scalar quantity. So mention moment of inertia is a scalar quantity. So here I have indicated these are equal in length A. Okay. Okay, I got two different answers for the first one. One answer states it's 11 and 24, and okay, another one has 11. I think 11 is the answer. Let's see. Okay, so first one, we had to take the moment about the moment of inertia about point O. So I O, for example, okay. So the mass 3 into distance 1 squared plus, yeah, 2 into 2 squared. So here 3 plus 2 into 2 squared for H. So I naught is 11 kg m squared. Okay, and then the second one. Okay, for the second one, I have got two different answers. We'll see which is correct. Okay, so here we want to take the moment about this point. So first this one makes mass is m, the distance is 2a squared. From here, the distance is a plus a, 2a, plus this mass m, and the distance is a squared, plus this one is m, and the distance is 0. Okay, so distance is 0, and this one is m plus m, and distance is a squared. So I equals 4ma squared plus ma squared is 0 plus ma squared. So I equals 6ma squared. So here key thing that you have to note is if the mass is at the axis of rotation, then it won't include to the inertia. Okay. Okay. So the next question. The following system is being rotated about axis. If I'm correct, the plural of axis is axis, right? Yeah. If I'm wrong, correct me. Okay. Is being rotated about axis. The following system is being rotated about axis, going through the points A, B, and C. A, B, and C, and their moment of inertia about each point. Moment of inertia about each point are IA, IB, and IC respectively. Right them in the ascending order. Write them in the ascending order. Okay. Mm, okay, let's take here 1 kilogram and here 2 kilogram and 3 kilogram. A, B, here point is A, B and C. Okay, so you have write IA, IB and IC in the ascending order. Here this point is A and here this is B, here C. Okay, I got an answer from Asha. It's correct. Very good. The question is, so here the system is there now. Okay, so the system is first being rotated by A. So when you rotate by A, the moment of, the axis of rotation is A. Okay, so that means you are rotating the system about this axis. Okay, and then if you rotate from here, then it has some moment of inertia, that is IA. If you rotate from B, then the moment of inertia is IB. If you rotate from C, then moment of inertia is IC. And you had to write these three in the ascending order. By the way, Aisha, your inequality is correct, but you had to write in the other way around, right? Because it says to write in the ascending order now. So starting from small to big, you had to write. Ida is not, uh, you had to check your answer again. Hirosh, not correct. Amra, okay. Mm, I will do this. So first I'll find IA, rotating about A. So when rotating about A, I have these two masses. Okay, this mass won't come because it's in the axis of rotation, right? Okay, so here 2 into x squared plus 3 into 2x squared. So here IA is equals to 2x squared plus 2 squared is 4, 4 into 3, 12 x squared. So IA is equals to 14x squared. And then I calculate IB. IB we have 1 into x squared plus 3 into x squared. So IB is equals to 1 plus 3, 4x squared. Then I calculate IC. So from here I have these two masses. So 1 into 2x squared plus 2 into x squared. So IC is equals to 4x squared plus 2x squared. So IC is equals to 6x squared. So we can see the smallest one is IB, and then IC, and then IA. So the answer is this. Here you can see now from A, the highest mass is the largest mass in the larger distance. So, I mean, to write this, you no need to write, check each value. Just you can understand now from here, if you consider the moment, the larger mass is at the far distance. So IA is the maximum because the largest mass is very far from the axis point. So IA will be the maximum. Okay. And then uh, when it comes to B, the masses are not far apart. They are compared to other two scenario. The masses are less distributed. It's closer. So therefore, IB will be the minimum. Okay, and then from taking IC, it has a value greater than IB. Okay, do you all understand? Okay, good. So you may have these type of questions also. Okay, I'll give you the other question. Uh, the next question. Okay. So it's a square. Each side 1 meter. And A, B, C, D. So I'm not giving the writing the question. The question, it's similar to the previous. The wording sentence are. You have to find I'll give the masses. Let's say here 1 kilogram, and this is also 1 kilogram, and 3 kilogram, and 5 kilogram. Okay. I'll ask you one question before you're starting. Uh, let's say from rotating from A, the point from point A, the moment of inertia IA, and then this IB from point B, rotating about the axis going through B. That means now you have the uh, so it's rotating actually perpendicular to the plane and going through the point A. Okay. So that means if I have the rectangle like this, let's say this is square, Okay, so I rotate like this. Okay, perpendicular to the plane. Okay, because otherwise you may think rotating like this and all. No, we are rotating about axis going perpendicular to the plane. Okay, each of the points axis are perpendicular to the plane. Okay, I see I do. So I mention only that uh, the system is rotated through axis axis passing through points A, comma B, comma C, and C, comma B, C, comma D, and these axes are perpendicular to the plane that consisting all the particles. Okay. So now, for example, if it's a square, so in these edges the particles are there. So plane consisting all the particle means that plane. So you are rotating. So this is the rotation axis. It's rotating about that point. Let's say point A, like this. So point B, from here you are rotating. Okay. Okay. So here, okay, I ask you a quick question. Out of IA, IB, IC, ID, which one is the maximum? You have to quickly say that. Which one has the maximum value? Yes. What about the others? Uh, no, not ID. Out of IA, IB, IC, and ID, which one is maximum? Yes, IA. Because you can see from here, if you rotate from here, the largest mass will be at the far distance. So, and the minimum is ID. So the maximum I is IA because the larger mass will be farther distance, and the minimum I will be minimum moment of inertia is ID, rotating about D because the larger mass at the axis of rotation. Okay, so here you had to write these in the ascending order. Okay, so that one you can try later. Okay, and send your answers. Okay. By the way, so today we were planning to complete every note related to rotation motion so that the lesson will be done and dusted. Okay, do you need a break? Now we started at 9:15, now it's 11:15. Let me know in the chat box because our session will be 4 hours long. So let me know, do you need a break for 15 minutes or 10 minutes? If you need a break, drop a message yes, and then time duration 10 minutes or 15 minutes. If no means no. Okay. This is not circular motion. Circular motion is different. This is rotation motion. But when we discuss about circular motion, we have to use this equation of motions and all. Yes, students, I'm expecting an answer for my question from you all. So, do you need a break or not? For me, it's okay. Anything is okay. Uh, I can continue another 2 hours at a stretch. For me, it's totally fine. Okay. How about others? I got only one. Okay. Two response I got as no. No need of break. And there are another 4 students. Hirosh, I will let you know about that after the class. Maybe we can have it. No. Okay. So 3 no's, 4 no's. Okay. Good. I'm so happy for your, response. Yes, I can see how you are very dedicated to study. It makes me really happy. Really. Thank you. Okay, then we'll continue. Okay. Anyway, this question is I will leave it to you as homework. You have to do it as homework and share your answers, and I'll check and let you know whether your working is correct or wrong. You can send me through WhatsApp. All of you have to do it and send me within today uh, after the session. Okay, send it through the WhatsApp. Okay, right. All right. Okay, so then we have to discuss the next topic, the moment of inertia of common objects or regular shapes of objects. Okay, regular shape or regular objects. Okay, let's start from the ring. So I'm going to derive this relation, the moment of inertia of the ring. Okay, so we will derive that. Okay, so here we consider a ring where the thickness is, it can have a thickness in, wait, hold on, I have a ring. Okay, so with thickness is, it's a very thin ring. Okay, thin, thin circular ring, thin circular ring. Okay, so moment of inertia of a ring. So total mass, let's say capital M, and the radius R. Total mass is M. Okay, so we are going to derive the moment of inertia of this ring. But we know that definition for moment of inertia is I equals sigma mi ri squared. Okay. So here what I'm going to do is I'm going to cut or divide this into small parts. I mean, like n number of masses. I can divide this into very large number. So n is very large number because I want to have each mass is like a point particle. So I will divide this ring into uh, n number of parts. Okay. Okay. So first let's start with the topic, the moment of inertia of a thin circular ring of mass capital M and radius capital R. Okay. So the first thing, let's divide the ring into large n number of n within bracket large number of pieces. Okay. So therefore mass of a one piece of a piece or a small mass is equals to total mass is capital M divided by n. So I can write, so mass of a piece simple m equals m divided by n. Let's divide the ring into n number of pieces which have same mass. Okay, so we divide into or equal pieces, n number of equal pieces. Okay. So then that we are rotating about this point O, the center. So the ring is rotating about the center O. So then this, if I consider here the particle, say has mass m, okay. So its inertia, I can write therefore equals to the mass is simple m times the distance is r squared plus, and then I can move to the next one. That mass is the small particle mass is m, the distance is r. So we have mr squared. So we have to add all the mr squared. Okay. So how many terms will be there because we have divided into n? How many terms will come? Yes, since we divide n number of particles, so we get plus mr squared. So here we have n terms. So that now, for example, a plus a, we can write as 3 into a. If 3 terms, we write 3 into a. So here then I can write I equals to n times m r squared. So I equals n times m into r squared. What is n times m? What is this simple n times simple n? Yes. What about others? Yes, mass of the ring. So that is the total mass, which is capital M. Therefore, I equals mr squared. Okay. So this is the moment of inertia of a ring having a mass capital M and radius r. Okay, you can write this down. You guys can write down. Give me a minute. I'll drink water and come. Okay, give me a minute. Okay. Actually, I wanted to go to washroom, but I didn't say. I said I want to go have water, but unfortunately, washroom is already occupied. Okay. Anyway, so can you explain the last two steps? Okay, sure. Here, now the moment of inertia about each mass about this axis O, we write as, so we have to take this mass m into distance m r squared, and then the other mass is m, and its distance is r m r squared. So likewise, we have to add all the particles. So since we have divided this ring into n number of pieces with equal mass, so there will be in terms. So m squared, m squared, m squared, we have to add everything. So there will be a number of terms. So that one we can write as, now for example, we know a plus a plus a plus a. If we add the same thing 4 times, we can write as 4 into 8. So we are adding the same thing n times, therefore n times mr squared, and then n into m. So you can see from this relation here, if you multiply this n to the other side, it will be n into m equals capital M, which is the total mass of the ring. So therefore, the inertia, moment of inertia of the ring is given by mr squared. Okay, then here it is actually, uh, it is rotated not like this. If I have a ring, do I have no? Which, okay, so here let's say this is a ring. Hope you all can see. So this ring is not being rotated like this. So it is not rotating like this by now here it's rotating like this. Okay, like rotating a wheel. Okay, so the axis doesn't move. I hope you all understood. So when we rotate the ring like this, then the moment of inertia about the center is given by I equals mr squared. But if in case we are rotating like this, it has a different value. Okay, because you can see the distance will change for each masses. Okay, so in that, but we don't have such thing in our syllabus, so we have only this case. Okay, any more questions regarding this? Okay. So actually, this is a continuous object. The mass is continuous. So therefore, I is, I'm doing just for those who are doing combined maths, you will be doing integration. So here we can write this as r squared into dm. The mass is only we have divided into small parts. So r squared is constant. We can take out integral dm. Okay, so if you integrate this total mass from here to here, it will be the total mass. So I will be equals to mr square. Okay, this expression work. Okay, fine. And the next thing will okay. So we'll do, okay. The next one I will derive for a thin cylinder. Okay. So you can write the topic, the moment of inertia of a thin hollow cylinder with no base or lid. Okay. Okay, so let's take the radius R. Radius is R and height height H and height H and the mass. Total mass I take capital M. Okay. So here I want to find the moment of inertia of this about this axis. Okay, so here what I'm going to do is I want to now find the moment of inertia of this cylinder. Okay, so it doesn't have a lid or base, it only the curved surface. Cylinder with only curved surface. Okay, so cylinder with only curved surface. So I want to find the moment of inertia about this axis. So you can say the XY axis, about the XY axis. So this is rotating in this direction, let's say omega. So I want to find I. So I is, we know by definition, sigma mi ri squared. Okay. So now here, what I'm going to do is, I'm going to divide this uh, into, uh, I'm going to cut this into layers so that I get rings. Okay. Let's say, so I cut this into small layers. So it looked like a ring. So I'll take considerable this. So let's say this thick height is x. So therefore I can find the number of rings. Now actually this I had to be a very small thickness, but in order to visualize, illustrate the situation, I have taken a considerable height for x. Otherwise x has to be very small. Delta x, like in max the limit is goes to very zero, goes to zero. Anyway, so then here n is equals to h divided by x, right? The total height divided by the thickness of one ring gives the number of uh, rings. Okay, so here this is equals to, I can write h equals n times x. Okay, so then I can write the I. I is equals to, now I have this ring. This ring has a moment of inertia. So I want to take the mass of this one. So I take this mass of each one is m. Okay. So each of these have mass m. Okay. So therefore m into the radius is r squared, m r squared. So then I have to add all the rings. Now here the next ring. So from bottom to here, every ring I had to add m r squared plus 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 m r squared. And then how many terms? I have cut this into n number of terms, n number of rings. Therefore, n terms will be there. So therefore, I equals n into m times r squared. So then n into m. So m is the mass of one ring. So the mass of this wall will be n times m. Therefore, I equals n times m is capital M. Mass of one ring times the number of rings gives the total mass. So that is also have mr squared. Okay. Raise your hand if you understood this. Yes, okay. So this is actually the total height is h, right? So if you divide into equal, x, each ring with x. Now, for example, you take 10 centimeter. So you divide into like 1 centimeter, then you get 10 pieces. No? So likewise, this height h we divide into x, then I get the number of rings. Okay. Raise your hand if you are understood. Hirosh. And okay, I think all good. All right. So by the way, this one is not there in the syllabus, but you have to give a conceptual idea. I explained this. The ring is there. Ring, they have asked you, might ask in the term exam. The derivation also they might ask. Okay, the ring is must. Okay. Okay, so therefore the moment of inertia of a thin cylinder also I equals mr squared. Okay. Okay. So the next one, the cylinder, the derivation is not necessary, but ring is must. Okay. So I think okay. So this is a ring about the axis, cylinder axis. So if the ring is also like similar to cylinder. Like if the ring you take a thickness only, then it's like a cylinder only, right? So this is a ring, actual ring. So I equals mr squared. For thin cylinder also I equals mr squared. Okay. And you had to memorize these. I will mark these are must. So ring and cylinder must. This is not must. And this solid rod. For example, if you have a rod like this, so it's half mr squared. This is also must. And this is also must. And solid cylinder and hollow cylinder. Solid sphere and hollow sphere. So this is solid sphere is 205 mr squared. This is also mass. And hollow cylinder. Can take this here. Okay, so this is clear. Okay, so here the moment of inertia of a rod, when the rod is rotated from one of the end, then it will be 1 over 3 ml square. We can derive this also. I mean, to derive this, we had to actually use uh, differentiation because the r squared is changing continuously. So, sorry, we had to use integration. So therefore, these derivations now we can't do in physics. Okay. Okay, so here this one, uh, when the rod is rotated about the midpoint, then it is 1 over 12 ml squared. So you can see the same rod, but here we are rotating by the midpoint, but here endpoint. When you consider the endpoint, the mass is distributed over large range. The distance is large, but the range is like half only. So you can see this reduced by factor of 4, 1 over 4, no? Right? So therefore, when the mass is distributed to large range, it has a large moment of inertia. I have been told you many times now. Oh, okay. Don't disturb. Okay. So here the moment of inertia, this is must, this also must. And then this is uniform circular disc of cylinder of radius r. Okay, so the disc, actually they have drawn here a cylinder. Uh, so disc is like this, wait, I'll draw a circular disc about this point. So this is the axis of rotation. It's rotating omega. So the disk is half mr squared. And then that is the same for solid cylinder as well. Okay. So the disk, circular disk, and solid cylinder is half mr squared. Okay. Now ring and the hollow cylinder with no top or base, only the curved surface is there. Then it will also have I equals mr squared. The ring and that one same formation because it's about the mass distribution, how the mass is distributed or within the range. Okay, so if you consider this ring, so all the mass is distributed at a circle with radius r. So here, if you consider this hollow cylinder with only the curved surface, the total mass is distributed in the same distribution. The total mass is distributed in the radius of r. So they have the same inertia. And then the disk and the solid cylinder have the same moment of inertia. Okay. And then moment of inertia of the solid sphere is 2 over 5 mr square. And the hollow sphere, wait, it's not given here. Wait, let me name the picture. The hollow sphere 1 over 2 or something like that. No, 1 over 3 or something. I'm not sure it. Two over 3 mr squared. So hollow sphere is 2 over 3 mr squared. Yeah, these are we had to memorize. Okay, thanks for sharing this picture. Okay. So only these you had to memorize. Okay. the solid cylinder, and this is not necessary. These parts are, this is no need to memorize. This is no need to memorize. This is you need solid cylinder and the ring or uh, cylinder with curved surface and solid sphere, and then the rod needs from the here midpoint of 1 over 12 ma square, from one of the end 1 over 3 ma square. Okay, and then hollow sphere, it is thin spherical shell. This is actually hollow sphere they have given. This is yeah, yes. So this is hollow sphere, hollow. This is solid sphere 2 over 5 and hollow 2 over 3. Okay. Hirosh, if possible, you can share this to the group. All right. So please note down. No need to draw. You can note down this equation because yeah. So these only you have to memorize. Ring. Okay. So ring. We have uh, half. Sorry, m squared. A point mass. So that is also m squared, and the mass of the mass is m. And then cylinder with only curved surface. Or you can call it as hollow cylinder with no top or bottom. So that is also mr squared. Okay. And then solid cylinder, solid cylinder, circular disc, so circular disc half mr squared, and solid cylinder half mr squared, and hollow sphere, is 2 over 3 mr squared, and solid sphere 2 over 5 mr squared, and then rod from midpoint, it will be 1 over 12 ml squared, where L is the length of the rod, and end point, it will be 1 over 3 ml squared. Okay, so these are the ones you should memorize. If other object means, they will provide you in the exam. Now, for example, rectangular shape and all, rectangular sheet and all, length AB, I think it is 1 over 12 A squared plus B squared, something like that. But these and all not necessary to memorize, they will provide. I think 2006 paper about satellite, they have asked the moment of inertia and they have given this equation. Yeah, 1 over 12 ma square. Yeah, I have to take mass. Okay. Okay, you can note down. So you note down this one as well. So I think the rod is being rotated about midpoint. So once rotated about midpoint here is the axis of rotation. So like this, omega, then I equals 1 over 12 m a squared plus b squared. This is no need to memorize. Just when you are studying this, make a balagni and like. Okay. All right. Shall we move? What is the fourth one? You mean here? Circular disc, half mr squared. Solid cylinder, half mr squared. Hollow sphere, 2 over 3 mr squared. Solid sphere, 2 over 5 mr squared. මේක මතක තියාගන්න මේ hollow නම් 3යි solid නම් 5යි. So if it's hollow, in the denominator it's 3, solid will be 5. Okay. You can take a screenshot. Okay. So the next thing, okay, so before that, now I'm going to show that this relation. Don't write the topic. Before that, I will do this. Now we know if we take a rod, okay. So if we take a rod, if we rotate by this end, so the I is equals to 1 over 3 m L squared, where L is the length. I write simple so m squared. So L is the length. If we rotate from here, then I is equals to 1 over 12 m squared. Okay, now what I'm going to do is, I'm going to take this rod here. Okay, I take this rod and I'm going to I will cut the rod into 2. So then each one will be have a length of L over 2. So now I have 2 rods. They are being rotated by their endpoints. Again, I take the 2 rods now, I keep merge it, and then rotate. So then I am rotating this from this point. let's say xy, rotating about xy axis, some angular momentum, sorry, angular velocity omega. Okay, now I'm going to find the inertia of the system. So I equals to, so I have this rod. So its mass now, if I divide into half, the mass will be half no m over 2. And this one also mass m over 2, where total mass is m. So then I can write here m over 2 times the distance L over 2 squared. And then this one also makes a moment, no? Okay, so then it is mass m over 2 times L over 2 squared. So then I have here m over 2 times L squared over 4 plus m over 2 times, sorry, wrong. If I rotate the rod about this end point, I have this 1 over 3 factor, no? So 1 over 3 into the mass, because I take this rod and rotate by its end point. Then its moment of inertia is given by 1 over 3 into mass is m over 2 times the length of the rod is L over 2 squared plus 1 over 3 into this one into mass m over 2 into L over 2 squared. So I have 1 over 3 into m over 2 times L squared over 4 plus 1 over 3 into m over 2 times L squared over 4. So if I add these two, both are same, no? Same terms. Here also same thing. So I can write 2 times 1 over 3 into m over 2 into L squared over 4. So this 2 and this 2 cancel. So we get I equals m 1 over, sorry, here 1 over 3 in the denominator we have 4 here. So 1 over 12 m L squared. So we get the same equation here. Okay. So you can put a note, okay, just to understand to our next topic. So this is actually what? Combining two rods. Okay. Okay. So our next topic is the moment of inertia is compound objects. We take two objects and compound it or join them. Then add them and then want to find the moment of inertia about the different axes. Okay. So raise your hand if you understood. Okay, good. You can write this down. Can you give me that previous 1 minute? I will be back soon. Okay, so write down the topic now. The moment of inertia of compound objects. Okay, now let's do example 1. Let's say I have a disk of radius r, and it is rotating about this axis. It's rotating in this direction. Okay, so we know it has a angular momentum. Sorry, so we have a, it has a moment of inertia. So that I is given by, let's take the mass is capital M. So I equals m naught squared, right? The moment of inertia of a disk is half m naught squared. For a disk is half m naught squared. Okay, so now here what I'm going to do is I take a ring and placing on it as a placing as concentric. That means the centers of the disk and the ring coincide, same center point. So let's say this one has a radius r over 2. Say this radius is r over 2. Okay, and then mass of the ring, let's say as m. So the moment of inertia of this compound object, okay, is, so we have a disk rotating and it's half into the mass is m, and the radius is r squared, plus also we have a ring. So we ring, the moment of inertia we know mr squared, no? For a ring, I ring. So I is, sorry, here mass is m, simple m, times now radius is r over 2, r over 2 squared. Therefore I equals half mr squared plus 1 over 4 mr squared. So I can take 1 over 4 common, or I take 1 over 2 common. So I have within brackets here m, here half m into r squared. So this is the moment of inertia of this system or the compound object rotating about this center. Okay, this is example 1. And another example, let's take another disk. So it's rotating about this axis. Mass is m and the radius r. Let's keep a mass somewhere here. Yeah, let's keep a mass on this disk, rotating disk. So the mass is m, and this distance, let's take r divided by 3. So then I is equals to the disk of mr squared plus the mass. So it is mass times the distance squared. So r over 3 squared. So therefore I equals half mr squared plus simple m here, simple m r squared over 9. Okay, did you understand? I think there's nothing much to, it's not complicated, easy to understand, right? Okay, you can quickly write down this. And I'll give you a couple of questions. Okay, so I'll give you a question. Find the moment inertia. So first, I say I have a okay. Say I have a cylinder. Okay, so let's say the radius is r and it is rotating about the center. Okay, so the mass of this is the top. So it's like a disk, right? So its mass 2 kilogram. Radius r is I give r equals 1 uh, or 10 centimeter. Okay. And this one mass also I take 2 kilogram. And the mass of the curved surface, it's a hollow cylinder. So hollow cylinder. So the mass I give you 5 kilogram. Okay, quickly find the moment of inertia about this axis. Okay, I got an answer. What about let's wait for this answers as well. Good. So let's start this. I got two answers so far. One is 700, the other one is 0.07. I think someone has messed with the units. We'll see. So, i.e., the moment of inertia of a disk is half mr squared, half into mass is 2 into radius is 10 centimeter in meters. We had right 0.1 squared. Okay. So that is a moment of inertia of one disk. So in the bottom also we have such a disk. So into 2 plus the moment of inertia of the curved surface of this hollow cylinder. So that is again will be mr squared. Mass is 5 into the this radius is 10 centimeter. Therefore it is 0.1 meter square. So this 2 and this 2 cancel. So I equals 2 times 0.01 squared is 0.1 squared is 0.01 plus 5 times 0.01. So the answer is 7 times 0.01. So I equals 0.07 kilogram meter square. So that is the answer. So I equals 0.07 kilogram meter square. Okay. And you can write down. Okay. So write the next question. Mm, a wheel is made of a wheel is made by a material having a linear density of sigma. Linear density of sigma as shown in the figure. As shown in the figure. The radius of the wheel is R. Show that the moment of inertia of the wheel about its center axis is mm, hold on, I equals okay, or else I can write the question as derive an expression for, I don't know what is the final expression, so I'll change the question as derive an expression, derive an expression for the moment of inertia of the wheel about its center of axis in terms of r and sigma. Okay. Derive an expression for the moment of inertia of the wheel about its center axis in terms of r and sigma. Okay, you can start now. So the linear density means because it doesn't have a thickness. It's a all like line. I mean linear material. Okay, so the linear density means, for example, let's say this is a material, the mass m and the length l, and linear density will be sigma is equals to total mass divided by length. So the linear density is the mass per unit length. Mass per unit length. Okay. Okay. You can start this question. Okay, I hope you are continuing with the question, reaching the answer. And again, I will start because I don't have much time. All right, so here we want to find the moment of inertia about this point. Let's say O. So I want to find about O axis. Okay, so we have here. Uh, so here you can consider either uh, 12 rods. No, 1, 2, 3, 4, 5, 6, 7, 8. 8 rods rotated by its end point. Okay, or as 4 rods rotated by its midpoint. So I consider as 4 rods rotated by midpoints. If you consider either way, you will at the end you will get the same answer only. Okay. One, you can consider 8 rods being rotated by their endpoints, or 4 rods rotated by their midpoint. Okay. So here I'll do that. So here. Um, so anyway, either way you will get the same set. So here I consider 4 rods rotated by their midpoint. So when rotating by midpoint, it will be 1 over 3 into the mass. The mass of the rod we don't know, we had to write in terms of linear density, because the mass will be equals to density times length. Okay, because the density is equals to mass divided by length, therefore total mass is equals to density times length. So the density is sigma into length. So length is then 2r. Okay. Now if you consider as 12 rod, 8 rods rotating by midpoint, then you have to take the length as r. But here I'm considering 4 rods rotated by the midpoint, then length of the rod is 2r. Did you all understand that? Is it clear, guys? Raise your hand if you understood, or if anything confusing and mention didn't understand. Okay, you can raise your hand. Amra, Abhiushani, do you understand? No. Okay. All right, then I will do this question in the both the methods. Okay. So you can compare. Yeah, I think it's better if I can do in both methods. Okay. So I think you have written the questions now because I need the space. So I will raise the question. Okay, so this method one. So method one, I consider four rods rotated by their midpoints. Okay, so then I equals to, so then if a rod is rotated by the midpoint, the moment of inertia is given by 1 over 3 into mass times the length squared, right? So here 1 over 3, the mass of this will be the density times linear density times the length. So the length of this is from here to here, the length is 2r into 2r 1 over 3m, and then the length squared. So the length is 2r, so I have to square this 2r squared. So that is the one rod. We have such four rods. So multiply by 4. 1, 2, 3, 4. So four rods are there. Sorry, midpoint. So 1 over 12. Yes. From the end point only 1 over 3. Midpoint means 1 over 12. Thank you. Okay. So that is the moment of inertia produced by these four rods. Plus, then we have this circular one. So its moment of inertia will be, it's a ring, so mr squared. So the mass is, we can write sigma into the length. So this length is 2 phi r. The circumference is 2 phi r is the length into the radius is r squared. Then we can simplify this. So here we get, so here 4 into 1, 4 into 3. So 1 over 3 into sigma into 2r into 2r squared is 4r squared. Okay, plus, so here we have, here the radius is r, capital R, it should be the circumference 2 phi times radius 2 phi. Okay, so here we get 2 phi sigma r cube. So therefore I equals, here 2 into 4, 8, 8 over 3, 2 into 4, 8, 8 sigma r cube plus 2 phi sigma r cube. Okay, so here 2 sigma r cube common, I can take that out. Okay, so I have here 2 sigma r cube. If I take that out, here I left with 5. Here I left with 4 over 3. Yeah, 4 over 3. 2 sigma r cube. So therefore, I can write I equals to, I'll take 3 also common out. So 2 over 3 times 4 plus 3, 5 sigma r cube. So that is the moment of inertia. That is one method. So the method 2, I consider 8 rods, 1, 2, 3, 4, 5, 6, 7, 8, 8 rods being rotated by their endpoints. So therefore, I equals 8 into, if rotating by endpoint, it is 1 over 3, and the mass of this sigma into length, sigma into now length is r. So this is the mass into the length squared, r squared, plus this term, same thing, 2 phi sigma r cube. because the circle part will be the same. Okay, so here we get then, uh, so 8 over 3 sigma r cube plus 2 5 sigma r cube. So here in this I take 2 over 3 common, and then sigma cube also I can take out. So here I left with 4 plus 3 5 times sigma r cube. So the same thing we get. So I think the simplification is easier when we take 8 rods rotating by their midpoints. Sorry, endpoints. 8 rods rotating by their endpoints. Okay. Second part is in the you mean the method 2? So this is midpoint. We consider the midpoint here. Midpoint. Okay, and then here we consider midpoint of into how many rods? 4 rods. The 4 rods. Let's make that one. So here endpoint into 8 rods. 2 5 sigma. Okay. So here the 2 5 sigma is common. I mean 2 sigma r cube is common. Okay, so you can see here 2 sigma r cube. Here also 2 is there. I mean 8 means 2 into 4, 2 sigma r cube common we can take out. And here this is the mass of the ring. So it's linear density times the length. So length of this is 2 phi r. So when you multiply with r squared here, it will be 2 phi sigma r cube. How do we get? Yeah, because it's the circumference of this, the length of this circle, no? That's the circumference that you find c equals 2 phi r. So this length is 2 phi r. Okay. So 2 phi r, r is the radius. So the mass is length into linear density. Okay. So the mass of this, let's say m. So m is density into the length. Length is circumference 2 phi r. So that's what the mass of the ring. Okay, raise your hand if you understand this. Okay, raise your hand if anyone didn't understand. Don't hesitate, or else you can drop a message. Yes, you may hesitate like others will know, no, when you raise your hand. So you can drop a message if you didn't understand. If you understood mine, fine, no need to pretend. All right, so then let's move on to the next chapter. Okay, so rotational kinetic energy and the work done. Okay. So energy I will come later. Let's move on to the angular momentum. Okay, so write the topic angular momentum. Angular momentum. So angular momentum normally we denote by letter capital L, and it's a vector. Okay, so write down. It is the moment. It is the moment of linear momentum. It is the moment of linear momentum of a rotating body. It is the moment of linear momentum of a rotating body. Okay, so now for example, let's say a particle is moving in a circular path. Radius, let's take R. So mass M, and then the tangential velocity we can mark as V. And this particle is moving actually with angular velocity omega. Right? For our explanation, let's consider um, a constant angular momentum. Okay, sorry, constant angular velocity. So it's moving with constant speed. Okay, constant angular speed or angular velocity. Okay, now we know if a particle have mass and velocity, it has a momentum, linear momentum. P is given by mass times velocity, and we can see the the direction of the momentum is in the direction of the velocity. Okay, right. And then also we can see as the particles move in this okay, it will move in this circular path, the direction of the velocity is changing. So velocity is changing means definitely there is a acceleration, but we are not going to discuss about that. It will be, we will discuss in the circular motion. Okay, so because we know if a velocity, like for example, is moving this direction 5 meters per second, and then it suddenly changed to another direction 5 meters per second. Velocity is a vector. It has both magnitude and direction. If one of the thing changes means the velocity is changing. Even the magnitude is same, if the direction changes means the velocity is changing. So if the velocity is changing means there is acceleration. Okay. So we can see as a particle moving in a circular path, its direction always changing, right? It's continuously changing the direction. So it always experience a acceleration. So that we will discuss about that acceleration in the circular motion, which is known as centripetal acceleration. Right. For example, if object is moving in a circular path, means there must be a centripetal acceleration. Now, for example, Earth is rotating, revolving around the sun. So the centripetal acceleration is the gravity between the Earth and the Sun. Now, for example, let's say I have attached a stone into a string and rotating. The stone is going in a circular path. So that required centripetal acceleration or centripetal force is the tension from the string. We will discuss about that thoroughly in circular motion. Okay. Anyway, so this is the linear momentum. So the angular momentum is the moment of linear momentum. So angular momentum L is equals to R times P. Now the moment of force. Now for example, moment of force torque. Torque is the moment of force. Is how do we write? D times F. Right. So this is a vector. This is a vector. This is also vector. So here three of them are vector. Okay. So here this is the moment of force is the torque. So the moment of linear momentum is the angular momentum. The moment of linear momentum is the angular momentum. R into PR is the radius. Yeah. Okay. So we can write L equals R times P equals mv, mass times velocity. Okay. So you can start writing this. Okay, I think my Wi-Fi data is over. Mm, hold on, I want to connect. So, can you give me 5 minutes? I'll try to recharge the Wi-Fi through online. Hi, all, can you hear me? Hirosh, can you hear me? Hello. Okay. Uh, so shall we continue the remaining part in the evening class? I think it will take some time. I had to reload and then I had to uh, put the package and all. It's is it fine? Okay. So then today evening we will have the class by 8:30 or 9, uh, or maybe earlier. I will let you know in the group. Yeah, I will send the recording. Okay. Sorry guys. I wasn't aware of the package details, so it is over after 7:30. Yeah? Okay, all right. Okay then. And thank you for joining. Study well. And I think I gave you one question, right? You all have to do that question and send it to me, okay? So you have now 15 minutes now. The time's supposed to be, we start at 9:15, so 1:15. There's 15 minutes are there, so right after the class, you can write that question and write in the ascending order and send me your answers. Okay. All right, then see you. Bye. Take care.